So, good afternoon, everyone. I hope that you are all okay. My name is Carlos Quesada. I am an associate researcher at the University of Deusto in the city of Bilbao in Spain. And this session today is framed on the skills workshop sessions of the European Climate and Energy Modeling Platform 2022. And it's entitled High Resolution Time Series Processing. So I have to say that I'm really pleased with that great response to this workshop, as there were 40 people joined to attend. And I hope that you find this useful and you enjoy it. Um, Although I don't know the profiles of all the 40 participants, I imagine that this group is quite cross-disciplinary, and it's always great to have different opinions and perspectives from your side. So you are open to participate in the discussion. You can ask whenever you want, and I'll try to answer the best as I can. So it's possible that there are people here that have never programmed or have never used the R programming language, which is the language that we are going to use throughout this presentation. If so, don't worry, because for this session, it's not necessary to program anything in R. Although it's always welcome to have some programming skills or even understanding a bit of R, because it may help a bit to follow the session. But as I say, it's not necessary, okay? So what I'm going to present today is a methodology for segmenting or classifying households according to their electricity consumption, okay? This classification is based on cluster analysis techniques that are going to be applied to a database with several load profiles, okay? So the interesting thing is that these load profiles have a length of at least 1 year, and you will be able to play with them at the end of the workshop or do whatever you want with them, okay? So a load profile is just a time series indicating the electricity consumption over time of some house in particular, okay? As part of the processing, we will perform a technique called time series feature extraction, which is central in our analysis, okay? Why is it central? Because, I mean, the results of these segmentations can be used for improving predictive methods, such as the energy system models, or for optimizing technical and behavioral interventions, or for evaluating the impact on tariff changes. So the idea for this session is that we follow step by step the process that we have designed to analyze our load profiles, or time series, as you want to call them, of electricity consumption. So for this, what we are going to use is a Google Colab notebook that will allow us to run and modify the code in the R programming language for the different steps of our analysis, okay? So if I'm not wrong, I mean, I think that you need access for accessing Google Colab. I think that you need a Google account. So in case you don't have a Google account, you can always create one quickly right now, or just relax and use this session to watch and learn, okay? So if I'm not wrong, I think that you all can see the screen. So we are going to the link of our notebook. So if you click on your agendas, or I think that it's also in the chat, the link, you can find it. So if you go to here, that part here, you can find the link here, the link that we are going to follow. So click on it. And when you click on it, you will find, something similar to this. You will find this notebook, this R notebook here, okay? So this is an R notebook of Google Colab. Just for you to get a bit familiar with the notebook, I mean, it has a toolbar as in every application, in which you can save it in your local if you are interested in have it for use it in the future. And this is and you have other tools that you can use, okay? This is a notebook. So this means that you can add text as you wish by clicking on those interactive lines that appear, okay? And you can write text, and whatever you want, okay? And you have it just in case you want to have notes. You can also type any kind of code, but this should be code in the R programming language, okay? For example, print 4. And if you execute it using that button here, number 4 will be printed, okay? This is just R basics. But as I said, there's no need for you to program anything. You just can follow me, and that will be enough. So I'm going to delete this because, I mean, this is not part of our notebook of what I wanted to say today. Here, the lateral toolbar is interesting for us because here you can see the table of contents of what I'm going to explain, okay? And the third button here with the folder, it's also interesting because we are going to download a data set of 60 files, and all those 60 files will be downloaded here in one of the folders here, okay? The notebook will create a folder and all the files will be downloaded there, okay? So before starting, we need to install some packages in R. So the first thing that we are going to do is just clicking on that play button here, so that R can download all those packages that I have told to download, okay? This may take a bit of time. The estimated time is 5 minutes. It depends on the service of Google. So while we wait for it to be installed, we are going to do a short introduction of just to review some concepts of data science and machine learning, because these are going to be used during the presentation. Okay, so the data science process, we can talk a bit about it. It's depicted here as a 5-step process, starting from data collection, which is the process of gathering the data related to a particular topic of interest. For example, here, as you can see, we are going to follow more or less those 5 steps of the data science process. As you can see here, we are going to do the part of data collection, the part of data cleaning, the part of the exploratory data analysis that can be also called the data visualization, okay? And the model building, which is the feature extraction, the data segmentation that we are going to do here. Model deployment, okay, we are not going to do this, but I mean, you can consider that this document is part of that deployment, okay? So the data cleaning or data cleansing, as you want to say it, is the process for detecting and correcting or removing records in a table of samples in a time series that are corrupt or that are inaccurate. So, I mean, that it's getting rid of all the dirty data, okay? After the cleaning, the resulting data should be consistent with other similar data in the system. So the exploratory data analysis is the part that explores the data by means of visualization, okay? So that is the way in which you can explore the data while, or the data that you are going to use to work with, okay? The model building consists in applying machine learning techniques to create a model from the data, okay? We are going to see different techniques later on as we advance in our notebook. And finally, model deployment consists in putting our models into practice. That is showing results, generate reports, okay? More or less, as I said, we are going to cover all those 5 steps in our session, okay? This image is quite interesting because it's also providing some bars, so yellow bars, indicating different areas of knowledge. So we see, for example, that the fields of data engineering would cover the parts of the data science of collection and cleaning. We can see that data analysis cover cleaning and exploratory data analysis. Machine learning engineers work in those areas of model building and model deploying. And a data scientist work in all the 5 parts of the data science process. Okay? Now that we have mentioned model building and machine learning, let's look at this in a bit more of detail. Okay, so here below we have just a summary of some algorithms in the classical machine learning as we know it. So if you were so kind as to mute your microphones, because I mean the sound, I mean it's a bit, it doesn't let me to think as I should. Thank you very much. So this image shows the different classical machine learning algorithms that we can find and their taxonomy. Okay, here's a tree with just two main branches: one for supervised algorithms, and the other is for unsupervised algorithms. Remember that in turn, machine learning is a branch of artificial intelligence where you can find other branches, such as, for example, robotics or speech recognition, natural language processing, and so on. So supervised algorithms are those that require that our data is labeled in some way. Okay. From this labeled data, the classification and the regression algorithms can be applied. Okay. The other branch of classical machine learning is the unsupervised algorithms, which are those algorithms in which data is not labeled at all. Okay, so the main algorithms used in this branch are the clustering analysis algorithms, dimensionality reduction, those that make use of data associations. So clustering algorithms are the ones that we are going to use throughout this session. Okay, so remember clustering as the main point to be followed in this presentation. And okay, just for finish this introductory part, let's talk a bit about a general overview of the challenge that we are going to solve here today. Okay, so what we are going to talk is the work that we have carried out here at the University of Deusto, and we are going to replicate it in this session today. Okay, so first, the challenge that we have been that we are going to solve consists in we have a large set of thousands of dwellings, each one generating a load profile, as you can see here, okay, which represents, as I said before, the energy demand over time. Okay, so you can see that different houses generate different load profiles. The differences between the load profiles are due to a lot of factors. For example, the size or the type of the dwellings, the socio-economic conditions of the people who live inside each household, the habits of consumption, and so on. There are a lot of factors that may affect or influence these shapes of the load profiles. Okay, so those load profiles are made of hundreds of thousands of samples, as you may imagine, and they may have different lengths. They may start or finish at different times. So each load profile is different to the other. Okay, so due to this, it's necessary to find a way to work with them in an efficient way. Okay, and this way is feature extraction. You can see here, feature extraction is a dimensionality reduction technique that computes a set of values from each load profile. Okay, you can see a series of values. We will see which are those values. Those values or features represent certain characteristics of the load profiles. By reducing the load profiles to a small set of relevant features, all the analysis that we will do later will be easier to perform. I mean, we have simplified a lot our computation. Finally, by applying some unsupervised classification techniques to the features, we can build our set of profiles of electrical behavior that we were looking for. So the objective is to classify or to obtain the different profiles of electrical behavior for all the households in our data set. Okay, that is the different electrical patterns of consumption of all the households. So in this session, we are going to see how to perform all these procedures, okay? So let's see if we have everything has been installed. Okay, perfect. So we can go on with the first part of our session. So we are going to start with the data collection. So the objective of this part is retrieving the data set of load profiles from our repository. Okay, all the data sets that you will be available to download now are just a reduced sample of a real load profile data set provided by a Basque energy provider called Goyener. The Basque country is a region in the northern Spain. Okay, so that company has provided us different electricity supply points that we can identify as households. Okay, and the repository we are going to work with is accessible. I have made it public for you, and it's indeed a shared folder, which is in Google Drive. If you click on it, you can see that folder in Google Drive. And as you can see, it contains the 60 files we are going to work with. They are CSV files, okay? If you click on it, you can see that, Google Drive is showing it as a table. And that table contains mainly timestamps, as you can see here. You can see that the data started in 2017 and finishes in 2018 for this time series in particular. And you can see the consumption as numerical values here. Okay, the consumption is in kilowatts hour. Okay, perfect. So this column, we are going to ignore it in this session because it's a bit meaningless for us. But I mean, we have worked with also this column, which means the self-consumption, but okay, don't worry about that, okay? So the first step is download this data set, which is here in the Google Drive, to our folder named content data, okay? So here, which is the folder content, a new folder will appear, which is called data, and all the files will be on it. So by clicking the two following snippets of code, all the files are being downloaded. You can see the process of being downloaded here. So it's going one by one, downloading and creating the files here. If you refresh, if you go to the second button here, you can see that the folder data is created and that the files are being downloaded, okay? So it's a process that takes a few seconds because they are 60 files that they are being copied to the local folder, but it will allow us to work with all the data, okay? So let's see how it goes. Okay, there are just 10 files left and it will be okay. Okay, the 60 files are already here. I hope that for you, if you are following the session, I hope that for you it's also okay, that you have received all the files here without any problem. So now we can work with the files, okay? The first thing that we are going to do is inspect them a bit. We are going to inspect them. In the following snippet, what we are going to do is just read the files as data frames. A data frame is a data structure in R, okay, that stores all the data in the form of a list. Okay, so we will have a list with 60 data frames containing our data. Don't worry about that because I mean this is just a specific thing that we are doing here so that we can work with the data more easily. Okay, so to do this, we just play the button here, and that's it. 3 seconds, and now we have in the variable data list, we contain a list with the 60 files, and we can now work with it. We work with them. So as I said, the values that contain its time series is a timestamp, just with the time and with the day and the time, and another column containing the energy consumption of each household in kilowatts hour. Okay, the files are different in length, and they also start at different end dates. Okay, let's inspect one of them. Okay, for example, here we are going to inspect the file number 44. Okay, so just by clicking here, it's going to show the beginning and the end of the file. This is really similar to what we have seen here, but with the difference that we are working now in R. We have it in R, and we can work with it to inspect it as we are going to do, as we are doing now, and to work with it as we are going to do. Okay, so we see that, for example, file 44 starts in 2017 and finishes in 2021. Okay, and it contains a lot of data on the consumption. You can modify this number just if you want to visualize any other data. Okay, since now we are working, so far we are working just with numbers. Okay, but let's do it more interesting. Let's work with visualizations. Okay, so the following step of our process is the data visualization. So in this section, the objective is to get familiar with the data that we have already stored in the file, in the variable data list. Okay. So what we are going to do is plotting the load profiles so that you can see how they look like. We are going to spot gaps of missing values because, I mean, as you know, all data sets, all the components, all the files of a data set may contain missing values. I mean, because several reasons. I mean, because probably the data collector was not working at that moment, or because the author or someone that created the data decided to remove some points of the data. So missing values are very common in data science. So we are going to see here how to spot them and then how to correct them. Okay. And another interesting thing that we are going to do is to visualize the load profiles as heat maps. I mean, not as time series, but as heat maps that allows us to understand the load profiles in a most interesting way. Okay. So if you play the following snippet of code, this allows you to see the time series number 13 in our data set. Okay, so we are seeing it as a time series, as you can see here in blue, and we can see several things. We can say now several things from that time series. For example, that this in particular goes from mid 2017 and finishes at the beginning of 2021. Okay, we see that the consumption grows in winter and decreases in summer. Okay, this is probably due because people is turning heating on during winter, and then they are consuming more than during the rest of the year. Okay, we see that those peaks exceed in some points 4 kilowatts hour. Okay, so this value is exceeded in a couple of occasions. And as I said, we can see the drops in summer or in holidays. Okay, perfect. So if you wish, you can visualize any of the other 60 files just by changing the number here and pressing the play button. Okay, you see that different households have different load profiles. As you can see here clearly, you can see that how they change between the data files that we have. Okay, just for you to change it. I mean, you are free to change it. So in the following code cell, what we are going to do is to inspect the load profiles in detail but in this case for a particular time interval, because here we have seen the time series from the beginning to the end, but now we are going to do the interval that we want to show more narrow. We are going to narrow the interval that we want to show. Okay. In particular, we are going to take the time series 39. Let's do it here. Let's write 39 here just to see how it looks like in a general view. Okay, this time series. And we are going to narrow it just in 4 days between January 8th and January 11th of 2019. Okay, so this is more or less like this period here. So the time series at that period has this shape. As now we are seeing at a day level, let's say, and we can see, for example, that consumption is highest during midday and during the evening. For example, what is clear is that when people is sleeping, the consumption plummets a lot, as you can see here, here, here. And if you pay attention, you will see here that there are no circles. There are the points, there's a part here in which there are not circles, indicating that there are missing values at that point. Okay? So, as I said, some time series in the data sets may contain missing values, and one of our objectives is cleaning those missing values so that we can operate with the data properly. Okay, so another interesting way of representing the time series instead of this way, which may be a bit showing a lot of information, and we may be a bit overwhelmed with the amount of information that this is showing to us, we are going to show the data in a different way, okay? Using heat maps. So what's a heat map? Or what's the kind of heat map that we are using here? So we are going to represent the data in two-dimensional grids to show with different color or with different intensities of color the variations of the consumption. Okay, so those two dimensions that we are going to use are in the x-axis of those two-dimensional graphs that we are going to create. We have all the days in a year. Okay, all the days in a year. You can see here that we are showing 365 days plus one extra week, because we are going to use a way for expressing the days which contains 371 days. Okay, I'm going to talk a bit about now. Okay, but just for you to know that we are going to represent days in the x-axis, and we are going to represent the 24 hours in the day in the vertical axis. Okay, this is really great because this allows you to see at a glance the electricity consumption for a whole year of any household in our data set. Okay, so as I said, the number of days that we are going to use in the horizontal axis is 371. Why? Because we have been using a way of calling or to split every day. Because all the days have to be splitted into, well, this is important to say. What we want by doing this, since we are going to collapse several years, because you have seen that a time series contains different years. Okay, so do you have any doubt? No. Okay. If you have any doubt, you can interrupt me whenever you want, and you can ask me. Okay. So as I said, you have a time series containing different years, and the way of showing this is computing the mean for all the days. Okay, for all the years, all the the different years are going to be shown here as a mean. Okay. Um, in order to work to generate those heat maps, we are going to take each day and we are going to compute the week number and the day of the week. The week number will allow us to place each day into its correct week and the day into its weekday. Okay, we do this like this because we are interested in align all the days of the week. So because I mean in our work, it's really important that the weekends and the work days are well differentiated. Okay, so by doing this, we know that all those weekdays, which are 6 and 7, will be weekends, and those going from 1 to 5 will be work days. Okay, so this is a way of aligning all the days, having into account work days and weekdays. Okay, so once of that we have said that, we can try to show how it looks like. No, what we are going to compute the week number and the day of the week for any arbitrary date. Okay, so that you can see how it works. For example, I have chosen the date of today, if I'm not wrong. Yes, so 5 October 2022. This snippet of code, what it's doing is providing you the values of the week number. So it's telling you that today, the day of today, belongs to the week number 14. Okay, the day of the week is 3, indicating that it's Wednesday. And this means that today, the data corresponding for today would go in the column 276. Okay, so this is the way in which we have sorted or rearranged our time series. Okay, so the following code here, you can try with any other date if you want. For example, here I have placed the date in which Columbus discovered America. So you can try with any other date in this format. Okay, so you can see here that that day would go in the column 283. You can modify the year that you wish. I mean, this is free for you. I mean, you can place any date. If you want to try with another different month, which is not October, for example, March, oops, not the years 200, for example, like this, you can see that one day of March would go in the week number 11. Okay, okay, it's up to you to try any other day. But now that we have that tool, we are going to represent all the time series in our dataset as heat maps. So we can do this just by clicking here. Here, we are just telling R that interprets this function here, get heat maps list. And just here, this is also necessary for doing the part of visualization. This cell is, well, taking the output of the previous function and show it as the heat map. Okay, and finally we can display the heat maps in the data list. Okay, so just by clicking here, we can see how it looks like numerically. This is meaningless for us because, I mean, we cannot understand anything of fear, but I mean, this is for you to know how it looks like. And the visualization can be seen here for the time series 40 to 43. By clicking here, we can see how those heat maps look like. Okay, so here, as I said before, let me move this a bit below here. So here you can see in the x-axis the months, the vertical axis the hours in the day, and we can see the different consumptions in different intensities of red. For example, for this household, we can see that it wakes up at 7, 8, because I mean the consumption is starting at those times. So we see that in the morning is at home, but for example, when summer arrives, and they sleep during all the night. Okay, so this is the kind of things that we can assume when we see this kind of graphs. So those graphs are really nice because all the time series of consumption can be represented and can be visualized as a whole in a glance. Okay, so why are they different? Because there are different kinds of households, as I said before. We will be talking about this at the end of our presentation, okay? In which we will analyze the different types of consumption that we find here. The thing that we have to do now is just use these tools to obtain the different consumption patterns of our dataset. Okay, but for doing that, we need to perform some data cleaning, as we're going to do in this section of data cleaning is imputing all the missing samples. That's to say, correct the missing gaps that we have seen that there are some of them. We are going to do an extension of short time series, because I have to say that there are time series that are not as long as we wish. I mean, for example, you have seen some of them that are 4 years, but I mean, we have others that are shorter than 2 years, and probably this can be a problem for the analysis that we want to do. So there will be an extension of short time series, and we are going to do the correction of the daylight saving times. We are going to talk about this, but for example, there's a summer time which is affecting the measures. For example, here you can see a shift. This is produced by the 1 hour extra that they are giving us in autumn and that they are removing in spring. Okay, we are going to correct all these kind of things. Let's start with the imputation, or the imputation means to place a value where there were no value. Okay, we are going to work with the imputation of the missing samples. So this process is the process in which we will be replacing the missing data, and we will going to substitute it or replace it with real values. We are going to use this function here, which is in that package. I mean, for you, this is not so relevant. I mean, this is relevant for you just to know that we are going to use. I mean, if you have some knowledge of R, it may be interesting for you. If not, just this is not so important for following the session. With this imputation, what we are going to do is to locate all the values which contain an NA. NA means not available. All the not available values, we are going to impute them using samples which are close to that sample. Okay, let's say we are going to make use of the preceding and the subsequent samples to complete all those missing gaps. There are different imputation algorithms. For example, interpolation, last observation carry forward. We can compute the mean. Okay. In principle, we are going to have our approach is double. Okay. If the gap that we find is small, and with small we mean up to 8 hours, we are going to use an interpolation algorithm. We are going to see which are the samples which are close to the missing gap, and we are going to use it so that they look more or less like the neighboring samples. Okay. If the gaps are larger than 8 hours, what we are going to do is to use the LOCF, which is directly copying samples from previous dates. Okay, so this is what we are going to do. Why are we going to follow this approach? Because remember that we are interested in keeping the alignment of the workdays and the weekends. So this is why we are copying portions of the time series. Okay, and we are going to respect the three seasonalities that our time series contains. Those seasonalities are the daily seasonality, the weekly seasonality, and the yearly seasonality. This means that we observe patterns that repeat on the different days, also patterns that repeat in the different weeks, and also patterns that repeat in the different years. Okay, so by doing it like this, we are going to respect those seasonalities, which are going to be interesting for our subsequent analysis. Okay, so what this snippet of code is doing is looking at each time series if there are missing values. Okay, and if it finds and if it finds any missing value, it's going to place an NA on it, indicating that there's a not available value. Okay, by doing this, if we click here, we have what we have done is detecting all the missing values, and we can check it visually if we click here. For example, remember that time series that we were talking about before. I told you, okay, can you observe here that there's no circles? So now that we have substitute the missing values with NAs, now we can see that when we visualize it, we see clearly the gap. Okay, we can see clearly the gap. So now our efforts will be in correcting all those gaps using the algorithms I've been talking about. Okay, so um, by clicking this function, we are going to do that imputation that I was talking before. If the gaps are short, we are going to interpolate, but if the gaps are huge, we are going to copy, respecting the seasonalities of the time series. We click here, and finally, we click here again, and it tells, and those functions tells us that it has found missing gaps in the time series number 22 and number 39. This is not surprising because time series 39 is this one that we have been talking about. But it's nice that we get some confirmation that the missing gaps has been located. Let's do located and imputed. So because I mean, this process that we have followed now, it has found the gaps and correct them. Okay, so we can check visually that those missing gaps have been corrected just by clicking here. We can see in red the new values that our code has imputed to our time series, in that case, the time series number 39. If you wish, at home, you can try to locate the correction of the file number 22, okay? You will have to look for maybe you have to enlarge the range of dates here so that you can locate the red samples, okay? Okay, so now our missing samples are corrected, which is great. So let's continue with the second step of that data cleaning step or process, okay? So the extension of short time series. So in those time series that we are working with, you have seen that they have different lengths. We have seen that there are time series up to 4 years, but there may be time series which are shorter for what we are looking for. Okay. In particular, we are interested that all our time series contain more than 800 days. Why? Because in the following step, we are going to compute features for the time series, okay? And those features that we are going to compute require that the time series contains at least 2 years of data, okay? This is one approach that we have followed here. So what should we do next? So if we find a time series which is shorter than 800 days, what we have to do is just to enlarge it. what's the approach that we are going to follow to enlarge those short time series? Just copy portions of the time series just to obtain a time series which is longer than 800 days. How are we going to do that copying? Respecting, as I said, the seasonality, the daily seasonality. Remember that we always want to respect the work days and the weekends. Okay, so if we copy going just 1 year before, we would be making an error, because I mean we will be copying from a Thursday when we should be copying from a Friday. So we had to take a bit of, we have to be careful with that. And to solve that problem, what we are going to do is just copying from 364 days instead of 365, because that number here is a multiple of 7. Okay, so this is the approach that we have taken. There are many approaches that we could have taken, but I mean, for this presentation, we think that this is the one that can be understood the best. So this is the approach that we are going to follow here. Okay, so the function that we have created to perform this extension is this function here, which is shown in the following snippet of code. Okay, it's a long one because I mean it takes it has to analyze the time series, it has to check when if it has to copy or if not, and then if we execute the function here, it's working with it. I mean, it's a bit process consuming. It's going to take 10 seconds, okay? 8 seconds. It was faster than I expected. So we have seen that there has been 3, 4, 5, 6, 7 time series that have been enlarged or extended because they were shorter than 100 days, okay? One requirement for copying is that the time series is larger than 1 year, because if it's shorter than 1 year, it would be possible to copy. Okay, if this had happened, it would have been indicated here, but no load profile has been executed for being shorter than 1 year. Okay, so in that case, what we have done is just extend those 7 time series, and what we are going to see is just to visualize how they look like after that extension. So if we click here in the play button, we can see in green the extension that we have performed. Okay, the extension have been performed in the beginning. Okay, we have enlarged the time series from the left. Okay, in green you can see that the copy has been performed to the time series, and since we are respecting the seasonality of the time series, we can see that in the point in which there's an interface, let's say, the continuity is ensured. Here you can see that it doesn't look so weird when you see it in a general way. Okay, so if you wish, you can try to see the extension of other time series. For example, let's go with 60, for example. Let's see how the extension has been performed. Here we can see that, I mean, the gap was a bit large. Let's check with number 60. I don't know what it may happen. Okay, this is a strange time series that has been also enlarged. The enlargement has been also huge. Let's check, for example, number 28 to see what happens when we see that extension. For example, this time series was not so short, so the part that had to be enlarged was not so big. So this is a way to visualize how the enlargement has been produced. Okay, so now we have our time series with the missing gaps corrected. it has been enlarged for future processing. And then the last part that we are going to do in that data cleaning part is correcting the daylight saving time. Okay, because as we saw before, it's affecting a bit the way in which it's visualized. We can see here that the heat maps are shifted when the time is changed. Okay, here it's also clear how there's a shift uh, produced by the summertime. So we are going to remove this. How are we going to remove this? Doing a function that is doing this kind of correction. So if you can click here, for example, just to see an example. For example, here when you plot the time series number 34 before correction, you see it clearly, absolutely clear. You see that there's that shift that we have seen before. Here it's shown perfectly. Okay, so we are going to correct this. For correcting this, okay, we have created a function which is a bit complex because it has to analyze when the summertime starts and when it ends, and then it has to add an extra hour and remove it from the other time. So it's a bit tricky, but you don't have to worry about that because I mean, just all the code has been placed here. For you is as easy as clicking on the play buttons. Okay, so here we are applying the correction. It has taken 3 seconds to correct all the time series by the summertime, and we are going to visually check that this correction of the summertime has been produced. So here we were showing before correction. Now we are going after correction. So just by clicking here, we can see that the summertime has been corrected. Now there are no shifts, and we can see that that part that could be worrying for our subsequent analysis has been corrected. Okay, so this is how the data cleaning process of any data set works. It consists in make the data in a more walkable way. Okay, so now all the 60 time series in our dataset are ready to be analyzed or to be or to build a model for them to work. Okay, so let's continue with our first step. So if you remember, if we go to the table of contents, I told you that those parts here may be comparable to the model building that I showed in the graph of the data science process. So let's do it. Let's go on. Let's go to that part. Let's start with the feature extraction. So feature extraction, as I said before, when I was explaining what is the challenge of of our of our project, is a dimensionality reduction technique that allows you to compute a set of values that will reduce the time series to just a reduced set of values. Just this means that each of the time series will be assimilated to just a few values, and we can work with them in an easiest way. So let's compute those features. What are the features that you are going to use? How those features are defined? What can we expect of those features? Okay, so for computing those features, we have been working with a package called TS features. Okay, this is a package that can be found or that you can download using R. It's free, and it allows you to compute those features. We are going to work with those packages, with other packages that we require for compute those features. And one of the requirements that this package needs is that we have to convert all the time series in our data set as time series. Okay, since now they were as a data frame, okay, as a table. Okay, but we have to turn that table into a vector of numbers, let's say, into a time series. This is the data structure called time series in R, which is used or which is that you can work with it using the functions ts. Okay, this is for those of you who understand a bit of R. Okay, and here is the function that allows you to do this conversion from data frames to time series. I mean, this is just a few formalities that we have to do before computing the features using that package, the package TS features. Okay, so by doing this, we are loading that function into memory, into our workspace. And by clicking here, we create the list of time series of the load profiles. If before we had a list of data frames, now we have a list of time series. Imagine that you want to see how those time series look like. So we click here and we are seeing how the time series number 6 looks in this new format. Okay, as you see, all the timestamps they have disappeared. Okay, they have been substituted by our seasonalities in hours. Okay, I mean, this is just the formalities that we require for compute the features. And what are the features that I'm going to compute? First, we are going to try with the features by default used by that function. If you click here, you can go to the help of that function here. In this function, this help is showing all the features that it's computing for each one of the time series. So here you see that there are, I don't know if there are 30, 40 features by default. If you go to any of them, some description of that feature is explained. For example, this feature called first min AC. It's returning the time of the first minimum in the autocorrelation function. So you can find different kinds of features. I mean, most of them are really strange. Probably you don't have to know what they mean. But I mean, those are the features by default that may be useful for the analysis. And the first, and this is the first approach that we are going to follow. We are going to compute the features that are provided by default by this package. So we are going to compute the features. This takes estimated time of 20 seconds because this is a hard consuming, a high processing task. So while it's waiting, okay, it has been fast. Now we have our features computed. So now we can see a table of the values of the features. If we just print the first features that have been computed for each time series, we can see that they are just numbers that are replacing the long time series with that we have been working before. So let's say that one of the time series that we have seen that they are 4 years long and that it contains thousands of samples. We have now seen that they have been reduced to just a few 30 or 40 features. So now working with those values, each row represents a time series. Working with those features is easier for our computations, okay? Because they are shorter. Now, well, this is the explanation of what we have said. Each row represents the time series. Each column represents each feature. If we now plot one feature against the other, for example, here we are plotting the values for a particular for all the time series of the feature 12 against feature 13, we see, so now one of these dots is representing one of the time series, each of the time series. The 60 time series we are working with is one of each dots that you can visualize here. But now they have been represented using two of those features that we have computed. And when we do this, we see that those time series tend to cluster together. For example, we can see here a cluster, we can see here a cluster, here we can see another one. So this gave us an idea that probably we can cluster our time series by the patterns of consumption using this methodology. Okay, this is what we do, but instead of using the default features that we have seen here, because I mean, for us, those features are a bit meaningless because what's the crossing points? The crossing points are relevant for our analysis, or the flat spots. We don't know. So we thought of some features that could be interesting for our analysis. And those features that are interesting for our analysis is what we call the seasonal aggregates. Okay? What's a seasonal aggregate? A seasonal aggregate is the main value of our time series at certain time bands. Okay? For example, a feature could be, for example, the mean of the time series from 8 a.m. to 12 p.m. in the morning. For example, this could be a feature, the mean value at that time band. Or for example, which is the mean value on weekends in the time series, okay? Or which is even more complex, which is the mean value of our time series from 4 a.m. to 8 a.m. in summer. Okay, these kind of features. We thought of a series of time bands, and we compute our new features based in those time bands. Okay, we thought of 8 different groups of time bands. Okay, we created intervals of 1 hour, of 4 hours, of 6 hours. We were also using the days of the week, the weekends, the relationship between weekends and weekdays. But we found that the most interesting ones are those combinations of 4-hour intervals and season that I have been talking about here. Okay, so what we are going to do is, instead of using strange features that we don't know, we are going to compute the mean values for each time series at those intervals, at those time bands, and we are going to use those values as the features that we are going to analyze later on. Okay? Okay. For doing this, we need to compute. I mean, it's a complex way. I mean, it's a complex process obtaining those features. So what we are going to do next is clicking play in the following 5 code snippets. Okay, so the first, the second, as you see, they are long functions. The third, fourth, fifth. And then we are going to click here because it takes 2 minutes to be computed, okay? And in the meanwhile, I'm going to explain which is each one of those functions. While Google is processing our data, we are going to explain what are those functions here. So the first one that we have created is the one that we have created for obtaining dates from the dateless time series. Remember that when we have created the time series, we have removed all the timestamps. And for computing the mean values at time series, we have to recreate all the timestamps that the time series had before. Okay, so this is just a formality which is contained in the first function. The second function, which is called getBeans, is getting all those time bands that we created. Okay, it's separating, let's say, its time series into the different time bands for which we are going to compute the mean value, the average value. Okay, then the following function, get seasonal features from time series, is the one that it's computing those aggregates using the time band. So if first we separate it in time bands, and then we compute the means. I mean, as you can imagine, we didn't compute the means. We also computed the standard deviations, the medians, equivalent functions when you are computing medians. I mean, we computed a lot of functions, but here we are just going to show what happens when we are working with the means. Okay. The fourth function that we have been working with is a function for generate the names of the features. I mean, it looks a silly function, but it's quite useful because you have to put a name to your features, okay, to work with later. And the last function that we have clicked was the main function that allows you to compute and work with all the remaining four. Okay, great. Let's see if the computation of the features has been produced. Okay, so it just take 1 minute. Google is especially fast today because it's working at half of the time. Okay, so let's have a look of how the features that we have computed resemble. So they are more or less like the previous one with the defaults, but now they are not meaningless features. They are features that we know that we have created, and now we have them here. We have, for this demo, we have computed 500 features. Okay, we have here we have computed 500 features, but you should know that in our real case scenario, we have computed nearly 3,500 features to be sure that we were doing the things properly. Okay, great. So now that we have the features, let's do the segmentation. Let's work with those sets of features instead of the time series, and let's see how we can cluster them. Okay, so the next step is the data segmentation. Okay, the objective of this section is just to cluster the load profiles from their features, the features that we have already computed, the meaningful features that we have computed. So clustering is a technique that consists in grouping. It's like more or less that graph that I showed you before here, but with more, I mean, with clusters well-defined. We are going to look for more well-defined clusters, okay? So there are different techniques for clustering. There are some packages that allows you to cluster in a fast way in R, which are provided by the CL valid package that is available for everyone. In fact, we are going to load it here by clicking here. So all those packages that are good for us to cluster have been already loaded. Okay, and we are going just to explain just a bit what the different clustering algorithms, the different clustering algorithms that you can find when you work with that package. For example, we can find the hierarchical algorithms, which are the most basic clustering algorithms that creates a taxonomy, let's say, and then you can cut. Probably most of you know this kind of clustering algorithms. Then we have partitional algorithms, which, for example, k-means is also a very well-known clustering technique in machine learning. So probably you all know it also. And then we have used any other kind of clustering algorithms that ranges from unsupervised neural network algorithms, such as, for example, the self-organizing maps. There are also, we have tried with fuzzy algorithms, with model-based clustering. I think that the only one that we haven't tried is DB-scan, but it's a pending task in the future, okay? So in order to cluster according to the features that we have computed, we are going to apply three of those algorithms that I have been talking about. We are going to cluster using hierarchical algorithms. We are going to use k-means, and we are going to use the self-organizing maps. Which do you think that is the one that performs the best? So we are going to see it. I will keep the mystery right now, okay? So since those algorithms may relay, for example, k-means relay on random numbers, what we are going to do so that you all obtain the same results as me is setting the pseudo-random seed, okay? We can do this in R just by clicking on this button here. I have provided that number. So you all, if you all use that number, you are going to obtain the same results as me. So the features that we are going to take are those that we were talking before, those that combine a time band and a season. Okay, you can see here the names. They are indicating which times they are going from and to, and which season is taking. For example, spring, summer, autumn, winter. Okay, so they are 24 features, and we have added an extra feature, which is a ratio between the energy consumed in weekdays against the energy consumed in weekends. Okay, so by using those 25 features, so remember that we have reduced our long time series to just 25 values. So by applying clustering methods to those features, we are going to be able, if we are going to see if we are able to obtain the different consumption patterns in our data set of 60 time series. Okay, so we are going to call the CL valid function. Let's click it because the expected time is 10 seconds. So this function, if you look at the help of this function, you will find that you have to provide well, it's this function is really complete. That's why we decided to use this function. This function not only provides a clustering, let's say, it also provides different measures of validation that tells you if the clustering has been good or not. Okay, so this is why we decided to use this function. Okay, now we have computed our clusterization. As you have seen, it's not so fast as computing the features. And if you want to see what we have obtained, you can have a look to the outcome that we obtained, and it's this. This is a huge object, S4 object in R, that contains a lot of information of the clusterization and also the validation measures that we have computed. So all the data of our clusterizations that we are going to work with are here. Okay, we have said that computes for different ranges of clusters, but what we are going to do here, if this long snippet allows me to go to the next one, okay, what we are going to see is how it has worked when clustering for obtaining 4 clusters. Okay, so we want to see how the clusters look like, and we are also going to use heat maps to show the mean the mean time series of each cluster. Okay, so we have clustered our 60 time series into 4 clusters using those methods that I have been talking before, using hierarchical self-organizing maps and k-means. And we are going to visualize each of the clusters as a heat map, okay, as we saw before for individual clusters. But now we are going to use those heat maps to show the mean heat map of each cluster so that we can have an idea of how those clusters looks like, okay? So for plotting those clusters, we need that function that we put in the workspace by clicking on that play. And we are going to see how the results of the hierarchical clustering looks like. So just by clicking here, we are printing each one of our 60 time series. We are obtaining here in which cluster it has been placed. So we see here a lot of 3s. We see just a few 4s. In fact, that's just one 4. So we can summarize this in a table by clicking here. So we can see here that it has created just one cluster with just one element, which is not good. I mean, this is not what we expected, because I mean, we expected for hierarchical clusters that we obtain a balanced result here in that case. So let's see how the heat maps looks like when using the hierarchical clustering. So we see that heat maps. So the mean heat map in cluster 1 looks like this. This cluster looks like this. This like this, and this one, which contains only one element, is more similar to this one. So those are some hints that probably hierarchical clustering is not working as well as we expected. Okay, so we see that the clusters that we are obtaining are not so well balanced. We see that we obtain repeated clusters, so probably hierarchical clustering is not working with this. Let's go with k-means. Let's try to see if it's working as well as we expected. So let's click on the clustering. We have seen, okay, that probably if we click on the table, they are more balanced, but okay, we see that cluster number 4 is also not well represented. I mean, probably, I mean, if there are so many, I mean, a cluster with a few clusters probably is not working well. Probably it's taking the outliers of the time series. This is just a first hint that probably is not working well. So let's see how they look like. And we see also that the performance has been quite similar to the hierarchical clustering, okay? Because we see that this cluster should not be separated from this one. I mean, we expected that all the clusters were different. So let's try with the self-organizing maps. Let's see how the clusters that we obtain with it looks like. So again, if we compute and we obtain the table, okay, we obtain a result which is quite nice, because we see that it has created 4 homogeneous clusters, because I mean they contain near 15 elements in each cluster. So this may look like interesting, an interesting thing. So let's plot the clusters. Now we see that they have been properly differentiated. We see that among our 60 time series, the 4 possible clusters or consumption patterns that we can find, they look more or less like those. Now we will talk about what those patterns mean, but this is quite convincing, because we can see certain patterns that look quite understandable. They look quite nice. For example, you can see that there's no consumption here at those times. So this is a good point. I mean, probably those clusters are really, really good. So we are going to use some or self-organizing maps for our clusterings. Okay, we have obtained our 4 clusters, and now are those clusters well computed? I mean, what happens with the validation measures that our function provides? So, I mean, this is a topic that probably would require a longer discussion. I mean, this function is providing three types of validation measures. One of them is biological, because, I mean, this function can be also used when analyzing biological things. So we have discarded it. And you can check the different the different validation methods that we have computed. Okay, we are going just to show, just as an example, the silhouette width, which is one validation measure that it's quite used in machine learning, which just provides you with a graph that should be maximized. So the point which is in a maximum could be considered as a good clusterization. Okay, so it's indicating this validation measure is indicating that, for example, when computing hierarchical, probably you should not take 4 clusters, but 2 clusters, or probably 6. I mean, you have to also to consider the relative maximums. Okay, when you are working with k-means, probably it happens the same. Probably you have to compute, well, not 2, 3. It seems it's 3. With k-means is more or less the same thing. Probably you don't have to use 4 clusters for doing the clustering. Probably you have to use 3, or in that case 7. But for self-organizing maps, we see that, okay, 4 clusters is the exact number that you have to use. So probably also 2, but I mean, we are working with 4, and we have seen that it looks something interesting. So now that we have our patterns, that consumption patterns, just this section is just for you to tell you that when we have used the real data, we have been processing, instead of 60 time series, we have been processing 90 or nearly 90,000 time series from data sets coming from 6 different countries. Okay, not this data set that I have provided for you that contains only 60 from the north of Spain, but 90,000 time series. In these examples that I'm going to show you, I mean, they are preliminary results that we obtained a few months ago, in which we were working with just 24,000 time series. Okay, what we do with our patterns, with our clusters that we obtained, was to obtain a taxonomy. We applied a hierarchical method to obtain a taxonomy of the 40 clusters that we obtained, and these allowed us to group those consumption pattern by their meaningful meanings, or by their meanings, let's say. Okay, and we found that there were 4 large groups of clusters of consumption pattern. The first one, which is the most populated one, is about the primary residencies. They can be assimilated to primary residencies, and they were the 64% of our dataset. We could see also that we saw patterns with high consumption equipment that normally are connected at night. For example, I don't know, batteries, or probably they are charging the electrical car, these kind of things, and they correspond to the 30% of the time series that we analyzed. A 7% was of offices and businesses, and a 5% secondary residences. If we and we have also a 1% which was related to street lighting, which was a quite interesting pattern to see. But if we see those 4 large groups that we have been talking here, they correspond a bit, not a bit, but exactly with the 4 patterns that we have obtained here. For example, this pattern here corresponds with offices or businesses. Why? Because there's no people sleeping or living here. There's no people having a life at night. We see that the most consumption occurs in the mornings or in the evenings. For example, here in Spain, it's typical that businesses open in the mornings and also in the evenings, okay, with a pause in the middle. We see also that those businesses close in August because it's summertime, and they close also in weekends. So now you understand why we were so focused in keeping the daily seasonality, because those weekends appear here as no consumption at all. Okay, so this is indicating that those patterns correspond to offices and businesses. This one, the second pattern here, is clearly for main houses, main households, because I mean, you can see that there's consumption in the morning when people is waking up and taking breakfast. Then consumption is also intense at night when people arrive home after a long day of work, and they start to switch the TV on. We can see that the consumption slows down a bit in summer. Then that third pattern that we have obtained is related to those high consumption houses in which they load batteries at night or something like this. I have to say that those high amounts are so huge that they are a bit shadowing the rest of the consumption. Okay, and the fourth pattern is clearly for secondary houses that are inhabited in summer and in holidays. For example, you can see here clearly that the patterns are huge in summer, indicating that during the rest of the year, those households are empty because they are not inhabited. Okay, you can see also that, for example, those houses are habited in other holidays such as Easter or Christmas or even weekends, as you can see here. Okay, so those patterns that we have obtained are a reflection of the patterns that we have obtained with when we have computed our 90,000 time series. After that, what we have done is just classifying our patterns, our 40 patterns. We have provided some description as the one that as I have provide today, right now, just explaining a bit. For example, this pattern shows that there's no one in the mornings, that they are sleeping at night, that they use the weekends they used to stay at home during the weekends, that they do a breaks in August, and this is what we have done. So this is the end of this notebook. We have seen all the process that we have followed for obtaining the different consumption pattern from a series of raw time series in a dataset. And I hope that it has been useful for you. I don't know if you have any question. I imagine that if you have any question, this is time for answering. So I will wait some seconds for you if you want to do any question. If there are no questions, I'm happy that you have been waiting for this long session of 1 hour and a half. And if Sophia has nothing else to say, I imagine that I can close the connection and say goodbye to everybody. Isn't it, Sophia?
No, we're good. And I
Okay.
will stop recording.
Okay. Thank you very much. So that